Now, let's proceed with the quasi-classical case and try to apply this quasi-classical approach to the penetration through a field barrier, or I should call it as tunneling through a potential barrier. Now, if I consider the motion of a particle, now if I sketch down, this is my potential as a function of x, and if I think of the variation in potential like this, and this is my region 1, and this is my region 2, and this is my region 3, and these are my turning points x1 and x2. So I assume that the particles are, the motion of a particle of whose momentum, say, if I take that momentum as p1, for a free particle, this momentum is basically under root of 2me. And these particles are incident to this potential, say from the left with respect to me, and onto this potential barrier that have been interpreted here. So, and the energy of these particles that are incident on this potential is under root of 2me. And what is important here is that this E is smaller, it is less than that of the potential, the maximum value of the potential at the turning point x1. Now, if we think about it classically, the particle can no way penetrate inside this barrier. It's impossible classically for the particle to penetrate this barrier. But at the same time, there is the probability of corresponding this particle that tunnels through this barrier and coming out at the right of this graph. And so shall I say that there is a probability of the particles in the region 1 that are hitting this potential barrier, that are hitting this field, that they can tunnel through this barrier, and they can come out on the other side in the region 3. And ironically, the speed of the particle will be same as that of the speed of the incident particles that have interacted with this potential. So there is a non-zero probability of being these particles whose energy is less than that of this barrier potential in the region 3. That's not actually zero. There is some finite probability. And this is what is exploited in quasi-classical approximation to estimate out the probability, the particle's probability of passing through this barrier. Now, if I think of this region 1 and region 3, the particle is free in region 1 and region 3. And if I assign a wave function to the particle in region 1 as psi1 of x, and that will be ae to the power of I k x plus be to the power of minus I k of x, kx. Where this term, as we understand, this is indication of the incident particles, and this is giving us the parameter that gives us the measure of the reflected particles from this potential barrier. So we can call this incident beam of particles, and this term is the reflected beam of the particles. And in the region 3, or we can boil down this to AE to the power of I. Since I have chosen P1, so here I can think of K1. So this is iota P1 of X by H cross plus BE to the power of minus iota P1 of X by H bar. And because we know this P is H cross K. So this is my psi 1 of X, and now I can talk about psi 3 of X. Psi 3 of X will be AB, okay, so let it be E to the power of I P1 of X by H bar. So this is my wave function in the region 3, and this is my wave function in the region 1. And these A's, B's, and E's that we have here, they are representative of amplitudes of the incident, the reflected, and the transmitted waves. And now, if we think about the wave function in the classically forbidden region, I think x1, between x1 and x2, in this case, we have a classically forbidden region. So I must code down this as E, the total energy. So in this classically forbidden region, the quasi-classical approach, what we also call as WKB, it provides the answer. It provides a probabilistic answer. Since the particle's energy is smaller than the maximum of this potential, that means what we have here is this E is less than V max. It is less than V max. And if the potential V of X, the property that's exploited by this quasi-classical case, now if this V of X is slowly varying function of X, then we know how to write down the wave function that we have described in the previous video. So we can think of writing that wave function as, I would like to write that as psi 2 of X. So psi 2 of X will be, say, this is C by under root of P of X. And then we have EXP times minus 1 by H bar X1 to X P of X prime, its magnitude, then dx prime. And the other term will be d by under root of P of X, then exp times 1 by H bar integral, say, x1 to x, then P of X prime d of X prime. Now, and we better understand this P that we have here, this P of X is nothing but it's iota times under root of 2m V of, which point is it? It's x1. This is x1, so V of x1 minus E. All right, and thinking about this term, see, this term has an exponential, and this exponential is increasing, and it's increasing exponentially. And when the barrier is very wide, the barrier that we have been talking about, and this barrier is wide, then this exponential function automatically becomes unphysical, because having something exponentially increasing doesn't make sense physically. So what we do here is that we are considering the case where the barrier width is wide enough so that this whole term can be approximated to 0. And this is valid for as long as the physicality of the problem is concerned. So psi of 2 that we have, it only has the dependence on c by under root of p of x exp minus 1 by h bar integral x1 to x, then p of x prime and t of x prime. So we have three wave functions. We have psi1, and we have psi3, and we have psi2. Now, in order to write down the probability, the probability that corresponds to basically to the particle's motion through this barrier, and that's what is transmission probability. Transmission coefficient would be rather a right term here, and that is T. That is the ratio between the transmitted term, and so the transmitted we have E, the coefficient, and the incident is A, and this is the incident, and this one is reflected, so this is not going to play any role here as long as this problem is concerned. So I can think of this T as the speed of the transmitted particles times the probability density of the transmitted particles divided by speed of the incident particles times probability density of the incident particles, and this we can in simple terms write as E square by A square. So this is what we are going to calculate. We are going to calculate the coefficient E basically in terms of A. And what we are supposed to do in this case is we want the continuity equations. We want the continuity of the wave function. We have a situation like this, and this is our. So we want the continuity of the wave function at the turning points x1 and x2. So that's a prerequisite in order to calculate this transmission coefficient. So what we have is we have x1. So at x1 for continuity, what is important is that psi of this x1 must be equal to psi of psi1 of x1 rather should be equal to psi2 of x1. This should be the first condition, and the second condition should be the derivative, and that is psi1 prime of x1 must be equal to psi2 prime of x1. So these two conditions should be should be obeyed in order to execute some kind of continuity between the region 1 and region 2 at x1, and then between the region 2 and region 3 at x3. So in doing so, we have both the equations. We have psi1 of x, then we have psi2 of x is also there, so we can immediately write down the equation in terms of psi1 x1 and psi2 x1. So that's going to be what would be that would be simply a e to the power of I p1 of x1 now by h bar plus, I'm using the incident term and the reflected term, that's minus I px1. Instead of x, it has to be x1 here in this case. H bar is c by under root of some zeta 1. And when we take the derivative, after taking the derivative, what we will get is we'll get I by h bar, then p1 will be out, then inside, very simple, e to the power of I p1 of x plus b e to the power of minus I p of x1 by h bar is equal to, that will be I, okay, that we have got. So I is out. So here we will have the derivative. So in doing that derivative, we'll have zeta 1 by h bar under root of zeta 1, that to minus and c. where this zeta, as we understand, this zeta is nothing, this zeta 1 is nothing but I times under root of 2m. Since we are talking about the turning point x1, so that's why we have to write zeta here. So this is v of x1 here. It's not v of x. This is v of x1 minus e. So this is my zeta 1. The above two equations can easily be evaluated, very simple, using the boundary conditions at x1. Now, would like to exercise, we'd like to go for, I'd like to call this 1, I would like to call this as 2, and then I would be looking for continuity at x2. So where is our x2? So we have a situation like this, and we have a potential like this, and this is x1 and this is x2. This is region 1, this is region 2, this is region 3. Now we have been talking about this turning point, so we want the connection and we want the continuity of the wave function and its derivative. It's not only the wave function to be continuous. What is also important is that the derivative of this wave function should also be continuous. So in that case, I will have psi 2 of x2 equal to psi 3 of x2. That would be the case. All right. So similarly, we'll have psi 2 prime of x2 is equal to psi 3 prime of x2. So these two conditions have to be utilized, and we have to use them at this point. Okay, and when we do that, what we obtain is we obtain c by under root of, so I have to use here zeta 2, then exp times minus 1 by h bar integral x1 to x2, then p of x, and then d of x, and this is going to be equal to the transmitted one. What's that? That's e, then e to the power of I p1 of x2 by h bar. So this will be our equation third. And similarly, when you take the derivative of the wave function psi 2 of x2 and psi 3 of x3, we will come up as minus zeta 2 by h bar under root of zeta 2 c exp times minus 1 by h bar integral x1 to x2 p of x d of x. I'd like to close it. That will be I p1 of x by h bar e, the same term, e to the power of I p1 of x2 by h bar. So that's the case. So we have those four crazy equations. We'll not go into the details of doing some algebra. You can do that as an exercise in this case, and what finally we will obtain is that we would like to, if this is 3, this is 4, we would like to add 1 and 2. Now if we add these two, we can transfer these terms to the right hand side, and you can see that when you will add here, it must be minus, it cannot be plus, because you take the derivative, then you have to multiply this by the internal derivative of x1. So in that case, this will be minus, so you will have minus term here. So when you transform these terms on the right hand side of this equation, you'll be left with these, and if you add the two equations, these two terms are gonna cancel, and finally in dissolving down these equations, you will come across you will obtain C from them. So I should write down this adding 1 and 2. And transferring the terms, and you can see that there are some cancellations. We will have C equal to 2a, then under root of zeta 1 e to the power of I p1 x by h bar divide by, okay, this is divide by 1 minus A1 by IP1. So this is what we will obtain, and we will substitute this. On substituting this this value of C in this equation here, in this equation, if we substitute the value of this C in this equation, so this is 3, and if I call this 1 2 3 4 and 5, so substituting 5 in 3. So when we'll do that, what we obtain is we obtain an equation like this: E by A, which we are interested to calculate. That comes out to be 2 by 1 minus zeta 1 by IP1, and then you have under root of zeta 1 by zeta 2 e to the power of, so this is exp, then ip1 of x1 minus x2 by h bar, crazy equation, and then we have another exponential exp times minus 1 by h bar, integral x1 to x2 p of x and t of x. So in boiling down this, these quantities here under root of zeta 1 by zeta 2, we can take, if we scale it down, this whole scale. So we can think of having a square here. The square and root will go. This zeta 1 and zeta 2 will go inside, and this is then you will have here the complex conjugate of exp ip1 of x1 minus 2x bar, and this term will go, and here we will be left with this exponential function. Since we are calculating, we have squared it, that means this minus will turn into minus 1, will turn into minus 2. So we can write down the final equation as E square by A square, which gives us the measure of the transmission probability. That comes out to be, so see this 2, here we have 2, so this 2 will give us 4. So here we will have 4 in the numerator, and then we will have here zeta 2 by zeta 1 plus zeta 1 zeta 2 divided by p1 square, then exp, then minus 2, you understand, divided by h bar, then you will have integral from x1 to x2, p of x, and then t of x, and then closing. So this gives us the measure of the transmission. It gives us the measure of the transmission coefficients, and this probability that we have measured over here. We can boil down this. We can approximate. We have already approximated. We will approximate. So this is over t. This t is nearly equal to e to the power of minus 2 some gamma. And what is this gamma? This gamma is this whole shit that we have here. That is 1 by h bar integral x1 to x2. Then we have under root of 2m. We can write down now v of x minus e times tx. So this gives us the transmission probability. So there is some finite probability for these particles that are incident on this impossible potential that we have here. For these incident particles that are hitting this potential, and because we assume that their energy is less than that of this barrier potential. So classically it's impossible for these particles to penetrate this field, but quantum mechanically, using quasi-classical approach, there is some finite probability for these particles to penetrate this impossible potential for the classical particle. So this is, and these tunneling processes, they are common in the microscopic world. They occur within nuclei. As we know, they occur within nuclei, they occur within atoms, they occur in solids, they occur in metals, and if we think directly in terms of the nuclei that decay the particles known as alpha particles. They decay into the alpha particles, and they leave out their daughter nucleus. This process, this leaving of this alpha particle from the nucleus, which cannot be explained classically, because for alpha particle to penetrate this nucleus, it must have tremendous energy of the order of 24 to 26 mega electron volts. But when we calculate the energy of this emitted particle, it is only of the order of 4 mega electron volts. So classical physics has no answer for this decaying process in nuclear physics, but the same process can be explained using the idea of tunneling, using the idea of penetration through the field, which is impossible in the classical domain. And so these alpha particles, they escape, and it tunnels, it penetrates through the Coulomb barrier that's surrounding it. And this tunneling is not only confined to the decay of radioactive nuclei, it also occurs in metals. And when we talk about the metals, they are subjected to some external fields. Electrons can be emitted from the metals, and this is called cold emission, and these kind of emissions are also quantum mechanical. There is tunneling actually occurring in these kind of systems. So with this, I hope I tried my level best to get an idea of the tunneling phenomenon that occurs, even though these tunneling phenomenon cannot be explained using Newtonian mechanics, in which it's important for the particle to have energy greater than that of this maximum potential this particle is interacting.